These notes are over influential points and departures from linearity. In some problems, you're going to be given a computer output and you need to be able to interpret this. So in this example below, we have a computer output. For now, let's look at just the value that says constant. Anytime you see the word constant, you're going to think y-intercepts. And then anything else, so whatever this says, so in this example it says age, anything below the constant that you didn't identify as y-intercept is going to be the slope. Okay. This S value is the standard deviation of the residuals. And this R squared value is the coefficient of determination. So remember how effective our prediction line would be. Okay. Everything in this red box, it says these values will be used in Unit 9. For now, we ignore them. Okay, so for now when you see them, ignore it. We're not going to see it until the end of the course. Okay. Then it says R squared adjacent. Always ignore this value. We will not use this in this course. So it says using these 4 pieces of information, we can also get the following. Well, we can get the prediction line. So we know that y hat is equal to slope, so 2.1143x plus the y-intercept, so plus 3.371. We can also get the r value by taking the square root of r squared. So the square root of 95.4%, or in other words 0.954 as a decimal, would be 0.977. Okay. Influential points. So an influential point in a data set is a point that has leverage on the correlation and regression line. In other words, when removed, this point changes the regression line substantially. So influential point, when removed, changes the regression line substantially. Okay. An influential point might be considered an outlier if it does not fit the overall pattern of the data, but an influential point might also fit the data. Okay. So when we think influential point, an influential point could be an outlier, but an outlier cannot be an influential point. Okay, so in this example, it says here's some hypothetical data. Draw a scatter plot. So I'm going to sketch a scatter plot off to the side. This is my x, this is my y. So I have 1, 1, 2, 5, 3, 3, and this is just a sketch, so it doesn't need to be perfect. 4, 5, 5, 4, 6, 8. Okay. So for this one, if we were asked to find the regression line and find R, you could do it by hand, of course, or just use Desmos. And so we're going to go ahead and open up Desmos. Okay, and I am going to type in my hypothetical data by adding a table and then typing in all of my x's. So 2, 3, 4, 5, 6. Oops. And then my y's, 1, 5, 3, 5, 4, 8. Going to position that. So my graph should look similar to this, right? Because I just did a rough sketch. And then I'm going to click on this line with the dots, and that's going to open up my linear regression. So that means I have y hat is equal to 0.97x plus 0.93. I'm just going to round to 2 decimal places. And my r value is 0.777. Okay. Now it says remove the order pair 2, 5. So I'm going to go up to my table. I'm going to erase the 2, 5. I wonder if I was able to just take out this row, or they're going to make me move all my points up. Okay. Let me go ahead and move all my points up real quick. Again, all I'm doing is removing that 2, 5. Okay. So now when I remove the 2, 5, now I have y hat is equal to 1.23x minus 0.47, and then my r value is 0.914. And it says what happened to the slope, okay, and why. So in my original one, my slope was 0.97. Okay, so I had 0.97 and then it went to 1.23. Okay, so what happened to my slope? Well, my slope increased. And why did it increase? Well, if it had that big of effect on my equation, then that point, 2, 5, was most likely an influential point. Okay, then it says what happened to the y-intercept? Well, my y-intercept, it decreased. Okay, so I went from 0.93 to negative 0.47, so it decreased. And it decreased because the slope increased. So when the slope increased, it moved my y-intercept lower. Then it says what happened to correlation? Well, I had a 0.777 and then I went to 0.914. Well, my correlation increased. Okay, so correlation increased. Okay, this tells me that 2, 5 is not an outlier since it had such an impact on my overall regression line. So since it had such impact on that and it greatly increased my correlation, that tells me that 2, 5 was an influential point. And I remember back at 2, 5 and even go over here to try to visualize where that would be. 2, 5 was still almost on that regression line. Okay. Now, departures from linearity. So looking at an example, it says the number of certain types of bacteria after a certain number of hours is given in the following table. It says create a scatter plot on your calculator and sketch it here. So that's what I'm going to do first. Let me go ahead and just erase that. I'm adding a new table and I am going to type in all of my X and Y values. Five, 3, 3.5, 4, 4.5, 5, and then my Y values 1.8, 2.4, 3.1, 4.3, 5.8, 8, 10.6, 14, and 18. And then I'm going to hit that magnifying glass with the plus sign so I can make it look like how it looks like on here. Okay, and so if I was to draw a rough sketch of this, of what these points look like, I should notice that these points are no longer looking linear. Okay, so I'm going to keep that in mind. Then it says create residual plot on your calculator as well. So remember, in order to do that, I go back to my Desmos, I click on this line right here and it will pop up my linear regression, and then under residuals I click on plots. And then in order to help me visualize this more, I'm going to get off of the original ones, and I'm going to back this up so I can see it a little better. And my residual plot is going to look like this. Okay. So looking at this, it says, why is a linear model no longer appropriate? So if you look at this, notice how it doesn't look linear, but instead looks like exponential. So I would say, and let me make this a little bigger. Okay, a linear model is no longer appropriate because our scatter plot looks exponential. And our residual plot has a curved pattern. Okay. So this is what we think. What parent function does this scatter plot look like? Well, we said exponential. How do we undo exponents in an equation? Well, we use log. For this problem, you can do some trial and error, or you just know that this is the natural log. Okay, so what we're doing here now, it says we're using the same data, but it says between hours and the natural log of numbers. So what we're doing is we're actually going to take this whole value here and we are going to take the natural log of it. Then we're going to sketch the scatter plot and residual and see what happens. Okay, so I'm going to go ahead and pull my Desmos back up, move this off to the side, open this one back up. I'm going to turn off this one right here. And then for all of my y values, I am going to type the natural log in front of it. And again, why are we using natural log? Well, that's the inverse of exponential. So we're trying to cancel out this exponential. We don't want it to look exponential. We want it to look linear, because that is how we're able to best describe the correlation and make a prediction. Okay, so now when I do this, now look at this. Look how almost, well, not even almost, look how all of my points line up on that line. So if I was to draw this as a sketch, I would see that now all my data points look linear. And if I was to reopen up my residual plot, let's actually undo that. And then I want to do my residual plot there. Okay, and then I look at my new residual plot. Okay, what you should notice is that it is kind of all over the place. Okay, we do not see a pattern anymore. And this is what we want. We want to not see a pattern, because remember, in order to see if it is appropriate to match our data, we need to see that there is no pattern in the residual plot. So we would say, why is this a better model for the linear regression? Well, now the scatter plot appears linear, and the residual plot is scattered. Okay. The regression equation was transformed by taking the natural log of y. So this is the natural log of y hat is equal to 0.586x minus 0.0047. And again, we found this by, if you go back and look up at your residual equation, this was written on Desmos. So it says, use the equation above to make a prediction of what the quantity of bacteria would be after 3.75 hours. So x is equal to 3.75. We have the natural log of y hat is equal to 0.586 times 3.75 minus 0.0047. Okay, we would simplify this. We would get the natural log of y hat is equal to 2.1928. In order to get rid of that natural log, we would have to use its inverse e. So e to the natural log of y hat is equal to e of 2.1928, which means we have y hat is equal to 8.96. So that means 8.96 thousand bacteria is left after 3.75 hours. Okay. So it says there's many types of transformations available, and you can get really crafty and add in some constants. For AP statistics, however, we keep it simple, and here are some common patterns that you might see and need to transform. So the transformation here is, okay, the first one could be, well, we need to take the natural log of x and y. How do we know that? Well, if we take the natural log of x and y, we know is that it first contains the point 0, 0, and it appears to have a slight curve. Okay, so here's the point 0, 0, here's the slight curve. That's how you know you have to do both. Contains a non-zero y-intercept and appears to be exponential, then you only do natural log of y. Okay, a non-zero y-intercept. Okay, can't really see that here, but we can see that it also appears exponential. And of course, when you're doing these on Desmos, you can just play around with it. You just plug in all the different regression lines and see which one gives you a best fit. And for example, if a natural log gives you a best fit, then you know that you would have to take the natural log of one of these in order to get it to appear more linear. Okay, if it contains 0, 0 and appears logarithmic, then you would do the square root of x. Okay, so 0, 0, logarithmic. If it contains a non-zero y-intercept and appears logarithmic, you could also do the natural log of x. Okay. Again, we'll be able to test these and find out which one would be more appropriate when we're comparing the scatter plots, the r and the r squared value to the residual plots itself.